Why this iPad is tripping today. When you don't need it, it works great. These old files coming from. That's all right. All right.
Still in class.
Yes.
I got an interview.
All right.
With the job that you wanted.
I told you about.
Congratulations.
I told you how I had to.
All right. So today we're going to begin the section dealing with the synthesis of alkyl halides, right? And if you remember from part one, let me just give you an example. An alkyl halide is just a molecule that has a alkyl chain and a halogen somewhere in it as a functional group. All right, so it's not anything esoteric or brand new. We're just going to talk more about how to make them. Right, so we're going to basically deal with 3 or 4 methods to make these, but we probably won't get to all of them. We'll get to today. We're going to start allelic bromination, but let me show you some other ways. Some other methods. I'm just going to abbreviate alkyl halides as AH. All right. So one way you've already learned, right? If you take a an alkene plus a acid like HCl, HI, HBr, right? So what X is a halogen. You react that with an alkene, you get an alkyl halide as the product. Another method that you learned already is if you take an alkane plus a halogen and you uh, shine UV light on it. All right, you shine UV light on that alkane, you get what? Anybody? Anybody remember that reaction? Right, you get radical substitution, where you get a halogen here, here, and then one on the terminal carbon, like so. All right, so that's two ways that we've already talked about. Although, let me get that. I'm trying not to write on this line. Right, you get all 3 of these products in varying percentages. All right, so that's 2 ways. But now we're going to expand that and talk about some other ways. So today we're going to talk about allelic bromination. And I didn't want to send a video last night because it got late, and I'll just send it today. Uh, um, So today we're going to talk about allelic bromination. And I may move the exam to Friday, just depending on how far we get with this. But I'll let you know that by Wednesday. All right. You should still be studying. So allelic bromination happens when you take an allelic system, something like that, and add a halogen at the allelic site. Excuse me. So you have the allelic site is right here, right? And that's the site that's adjacent to your double bond. So when you do this reaction, the only site that gets brominated is that site right there. I'm not gonna go through the mechanism yet because I want to show you the other methods, and then we're gonna come back and focus on this for the rest of the class, right? So you need MBS, which I'll show you later, and light. Can somebody tell me? You can unmute yourself. Somebody tell me whenever you use light, what type of mechanism is that going to be? Now, we did learn that in part one. We learned about two different types of mechanisms. Can somebody tell me what they are? All right, so you're going to end up with, in this case, two products, right? And there's a reason for that, which I'll talk more about when we get to the mechanism. Anybody want to chime in about that? What type of mechanism happens when you use UV light? Right? Anytime you see UV light, that's indicative of a radical mechanism. What's a radical? Anybody? Don't all speak out at once now. We won't want the speakers to get overloaded.
Is when it's in like an unpaired electron?
Yes, a single unpaired electron. Yes. Thank you. All right. So we're going to talk more about this in a minute. And I'm going to send you a video after class to reinforce what we talked about today. So you got allelic bromination. And then the fourth method, which is actually three different reactions, is conversion of alcohols. All right, so conversion of alcohols into alkyl halides. Right, and then so with that, there are three different methods you can use with that. The first method is, let me do A. First method is addition of HX. So addition of HX. Normally you do this with a tertiary alcohol. Like tert-butanol. It works for secondary. All right, so you get a the halogen here gets transferred through what type of reaction do you think happened?
Oxymercuration.
No, not in this case. So you adding HX, right? And you're swapping out the OH with the halogen. What type of reaction is that when you swap partners like that?
Substitution.
Good. It's a substitution. Right. And this works on not primary, tertiary and secondary alcohols. And what type of substitution do you think it is if you do it on a tertiary? I think we talked about this. As a matter of fact, I know we did in part 1.
Is it Sn1?
Yes. Who was that?
Amaria.
Maria. Yeah, it is Sn1. It's a Sn1 type substitution. All tertiary substrates undergo Sn1 because why? Might as well push that point because we're gonna be talking about substitution soon too. Why is that? Why do you think? Think about the size. Right, the tertiary. What's the other mechanism that we learned? The other substitution mechanism. We learned Sn2 and what?
E1 and E2.
Okay, those are eliminations though, but you're right. So we also learned Sn1 and Sn2. Is that right?
Yes.
Is it too early?
A little.
Oh man, y'all got to get up earlier. Shake the dust off. All right, we'll come back to that, but it is a substitution. All right, the other method for turning alcohols into alkyl halides that we're going to study is addition of PBr3. So you take a secondary or primary alcohol. I'm just going to do a primary. You take 3 moles of it. And each one of those moles is going to react with the phosphorus, right? So you end up with 3 alkyl halides. And then ran out of room again. POH3, right? We're going to talk about it, so don't panic if it's not clear or if it's not making sense. It'll make sense when we discuss it. All right. And then the final method that we're going to look at for converting alcohols into alkyl halides is using thionyl chloride. And that's SOCl2. Right? It looks like this. All right, so this works with primary alcohols. It also works with secondary. But I'll just show the example with a primary. Again, all of these are substitutions where you swap out the the alcohol with a halogen. And the halogen, the source of the halogen is the thionyl chloride. Right? Let me change that highlight color over here. right? So all of these methods are ways to make alkyl halides. So what we're gonna, this whole section is gonna be making alkyl halides and then how to use them in specific reactions, right? So we're gonna talk about the reactions of alkyl halides too, substitution and elimination reactions, and then we're gonna talk about uh, using them for with organometallics to make organometallics and to do coupling. So let me give you, and if you look in the syllabus, all the alkyl halide stuff is outlined. How to with the synthesis part, the application part, and then the organometallic section. All that's in one section. So synthesis, and then we're gonna do the application. And with the application, we're gonna talk about go back and revisit substitution and elimination, and we're gonna talk about organometallics. Right, so this is a big section, but it's not anything that the only thing that we haven't seen is the organometallic stuff. Everything else we've seen, like just like today when we talk about allelic bromination, we've already seen radical mechanisms, and we've already done resonance on allelic radicals in part 1. All right, so let's go to, I got to switch, and I wish that other handout would have uploaded. Let me see if I can try it one more time. And no. Shucks. All right. So let me go back here and see if I can try something real quick. I probably need to do a new share. Anybody have any questions before we move forward? All right, great. So before I do anything with this, I want to show you, give you a generic example of allelic bromination. So let me put a date on this. Are you serious? I need no freaking laser pen. I'm gonna write on this. Black. All right, yeah. All right, so let me show you a generic example first, and then we'll come back to the main example. I need to add a page, and I probably can't. That's okay. Do it right here. Actually, you know what? I'll go back to here. All right. So with allelic bromination, let me just give a a very basic substrate. right? So it'll be this plus MBS, and I'm gonna shine a light on it. So I have, in this particular case, no, let me not do that. Let me not do that because that's gonna create a problem. I keep it basic. All right. So in this particular case, I have one allylic site. You can generally predict the number of products based on the number of allylic sites you have, right? So, so the number of allylic sites, that's going to tell you how many products you're going to get. Right. So you always take the number, you can take the number of allylic sites and multiply that by 2. That'll give you the number of products. So if you got one allylic site, then you're going to get 2 products. If you got 2 sites, you'll get 4 products. If you got 4 sites, you'll get 8 products, so on and so forth, right? So for this particular reaction, these hydrogens here, those are my allylic hydrogens, right? Because they are allylic, because they are at a position that's adjacent to the alkene, adjacent to the double bond, all right? So when I get my products, let me draw the products, and then we're gonna actually go through the mechanism. So the products are gonna look like this. I'm gonna definitely get a product with a bromine at the allylic site. Right here. But I'm also going to get a product here on the other carbon. Yeah. Right. And there's a reason for that. When we go through the mechanism, you're going to see why that's so. Right. So in the mechanism for the reaction, how many of you remember from part 1 when you did a radical reaction, what the mechanism was or is? When you do
I remember you had to take an electron from each hydrogen and draw the half arrow.
That's true. But when you were doing, like, let's say we were doing radical substitution, you had, how many steps did it take to complete that mechanism?
Was it 4?
It's 3. It's initiation, propagation, and termination. Is that right? Is that right?
Mm-hmm.
So for this reaction, since it's a radical reaction, it's going to go through the same steps. You're going to have an initiation step. And that's the step where MBS that's the step where MBS is going to give you your reactive radical, which in this case is, excuse me, bromine. So we're going to shine light on that, and we're going to break this bond. What type of bond cleavage is that? Anybody remember? There's only 2 types that we talked about. Working knowledge. Got to have working knowledge of part 1. Is it homolytic or heterolytic? Just sign right here. Sign your name right there. It's a homolytic. Remember we talked about homolytic and heterolytic. Anybody remember that from part one?
Yes.
Yeah.
So homolytic, I at first I thought it was hetero because wouldn't you be taking it from, I don't know, but homolytic, okay. Because I
Heterolytic.
thought it was hetero because I thought it was from two different atoms.
Mm-mm,
So that's
mm-mm,
not, no.
mm-mm. Homolytic means that they both become radicals, right? They both get one electron each.
Okay.
Heterolytic is when one atom takes all the electrons.
Okay.
But anytime you see light being used, that's always going to be a homolytic process because light cleaves bonds homolytically. It causes radicals to form. All right. So it's homolytic, and then all the bond formation is going to be homo what?
Gina,
Homogenic. Good. Who was that?
Kayla.
All right. Good. Thank you. All right. So in the initiation step, what we're trying to do is get or generate a reactive radical, which we have, right? Bromine is my reactive radical now. So that is going to go into the propagation step and do what? I hate this stylus. I hate this iPad. Anybody?
Something with the hydrogens, right?
Something, yeah, something.
Is there something with the alpha hydrogen?
Well, yeah, it's yes, the hydrogens that are adjacent to the double bond, the allylic hydrogens in this case. So in the propagation step, that's where you make new radicals, right? But you use the bromine that was formed in initiation. That's going to be your initiator. That's what's going to make your radical. So it's going to go in and start pulling hydrogens off. So if I have this as my substrate, zoom in, and I got two hydrogens on there. Let me change the colors. What did I make them red up top? I'll keep them red. And I'm reacting that with that. How do I show that at that step? Right. Remember in propagation, what happens is we do abstraction. Man, I promise you. I'm about to enroll in a pre-K, work on my handwriting. Right, we do abstraction. Or what is that? Anybody remember what that is? Abstraction? You just said it, but you didn't give me the term. It's removal of a hydrogen radical. Right, that process is called abstraction, and it's all homolytic and homogenic. So one of your side products is going to be, I need to move this over. One of your side products is going to be HBr. I need to move this down. All right. Screwed all that up. Right. So what do I get when I remove a hydrogen radical from here? What should I get? And how does it happen? You should remember this from part 1.
You're gonna get an H dot,
Mm-hmm.
or well, that's not the way you're supposed to say it, but
The H, yeah, a hydrogen rad, but it already paired up with bromine, right?
mm-hmm.
So bromine. Let me make sure you get what I'm saying with these arrows now. Right. Notice my arrowheads are single-headed. That means I'm moving one electron at a time. Right. And then one electron is going to go back to carbon. That's what abstraction is. It doesn't matter how big the molecule is, how many carbons. Abstraction always looks the same. Is the CH bond is cleaving, and then you making a bond between the H and whatever your initiator is. All right, questions about that? So what do I get besides HBr? Yo, man. I was talking to my dog. He's smacking. He's always smacking. All right. Is that what I get? Is that what the arrows indicate?
Yes.
Yes.
All right. So I get this is my new radical that I made in propagation. Now let me ask you a question. We could terminate that, but if you look up top, we actually get 2 products. So where do you think that other product is going to come from?
The terminal end?
Okay, yeah. Let me put it this way. The new product, the bromine ends up on this carbon right here. But I don't have a way to do that from this structure. So what can I do to this structure to put an electron on that end that I have highlighted? And it's something that I beat you down with for the whole semester that you should remember. Can I do a resonance form for that? Do I have a donor and an acceptor adjacent to one another?
Can you repeat the question?
Can this structure do resonance?
Yes. No. No.
I should do a poll. That's okay. It can, right? This is an example I gave you when we studied resonance. For those of you who took my class now, if you didn't take the class with me, but I know y'all studied resonance. But the way I gave it to you, I gave you 4 different examples. I gave you an allylic cation, an allylic anion, allylic radicals, and then I gave you a molecule that had the donor and acceptor on atoms right next door to one another, right? So 2 atom unit and 3 atom units. So this is an example of a 3 atom allylic radical, right? So you can see right here, let me erase this one. This is how your electrons are going to be shared over these three atoms, right? And if I put the put the arrows in, boom, boom. What's that? What does that mean when I show the arrows like that? Let me zoom in so I can make it more accurate. So what does this mean if I show an arrow coming here and one coming here? Now this is the first Monday in this class, but it actually feels like a Monday. I'm gonna help you out though. Doesn't that mean I'm gonna get this?
Yes.
Let me fix this arrow too. Should be coming from the electron. Do you see that the double bond, these two arrows here coming together means that the double bond shifted over? Right, so that resonance rearrangement, that's gonna give me another radical, a second radical. That's how I get two products, through resonance. Right, so now when I go to the termination step, oh shucks, sorry. Now when I go to the termination step, those are the two radicals that are going to terminate. It's horrible, right? Any questions about that? We about to do some refreshing. I shouldn't have to, but we are, because it shouldn't be church mouse quiet when we talk about resonance, because that's something that we talked about the whole semester. All right, so I'm gonna take this radical and I'm gonna take the other one and I'm gonna pair them up with bromine. And I'm gonna make that bond where the two radicals are. How's that gonna happen? Homolytically or homogenically?
Homogenic.
Mm. Good, you're right. So I'm gonna show a single-headed arrow coming from each atom, and that'll give me my two products. All right, questions about that? So we went through for Allelic bromination, you need an allylic substrate. And it's a radical mechanism. So we went through an initiation step, a propagation step, and a termination step. All right. Let me switch over to something right quick, something different. And let's do these examples. And this handout is in, come on, man, stop tripping. This handout is in the assignments folder, and it is, where's that eraser? I think it's called, it's Allelic Bromination in class exercise 2, I think. Don't worry about the date on it. That's the right assignment. All right, so let's do a little refreshing. All right, so let's look at each one of these. Each one of these is an allylic radical. Do you agree? And tell me why it's allylic. What's that term mean when we say that something is allylic?
It's adjacent to the double bond.
Adjacent to the double bond. That's what we're looking for. If that radical was here, we couldn't do anything with it because we couldn't do resonance. Remember, the donor and the acceptor have to be adjacent. They got to be right next door to one another. Otherwise, you can't do resonance. All right. All right. So where's my my unit? You see it right here? I need to change that. The pen is too thick. Right? Do you see it here? Those 3 atoms. That's where you're working. Right? So when you do resonance, you're gonna do here, here, and then here. The double bond is just gonna shift over to here. Right? You're just gonna shift it over, and then your radical is gonna end up here. All right. So then the resonance form should look like this. It's not gonna, the ring doesn't change, but the position of the electrons does. Can I do resonance again?
Yes. Yes.
I can. Where's my other acceptor? I can only go backwards, right? Because there's nothing on, so here's my electron. There's nothing on this side where I can share it with. You follow me?
Oh, yeah. Yeah.
All right. Let's look at the next one. Right here. You can see it immediately. You can see the allylic system right there. And so the first, right, you can see that. Sorry. I need to put him in doggy daycare. Right, so you can see I'm going here and here. That's going to shift the double bond over. And then this is going to put the electron here. All right, so then my resonance form is going to look like that. All right, can I do it again? Now, in this one is different, right? Because I do have another place where I can push that radical, that electron. Can somebody annotate that? If you can hit the annotate button on your screen, let me see if make sure you're able to do it. Annotate, yeah. Somebody put the arrows in on this one, and then we're gonna stop. I'm gonna send y'all this Allelic Bromination, and I'm gonna send y'all a refresher on resonance because it ain't clicking. Or maybe it's clicking and y'all just not talking. I see some arrows. Who's annotating?
Dr. Ross, I'm trying to annotate it, but I did arrows instead.
You don't have a pen? There you go.
Okay,
Use,
there it
use your
is.
pen. Come on now.
Um,
Okay.
and
Where's that one going?
okay, so the lone pair is going to that one, and then this double bond is going there, and then that's gonna turn into a lone pair.
Okay. I feel you, but you're not working with a lone pair. You're
Right
working
there,
with one electron.
that dot.
Yeah, that's only one.
No, I'm sorry. That's what I meant. Sorry.
Yeah,
Not a
if there
lone
was
pair.
a pair, it would be two, right?
Right.
Okay.
My bad.
So now the other question is, you got two arrows, but look at my resonance form on the left. I'm using three because I need to break that pi bond, and so in order to do that, I split it in half. So you need your arrow should look like this, where you go from here to oh sorry, wrong pen. Your arrow should go from here to here, like that. You see that? So then that's telling me I'm moving the pi bond there. And then this arrow comes here. Now your last arrow was accurate. It just should have been single headed, like that. Following? So go ahead. You can draw that. Draw what we would get from that. Let's see if you caught it. And thank you for stepping up to the plate to attempt it.
Can you draw the like the
Draw the ring for you?
yeah.
No.
All right.
You draw it. You gonna have to draw it on the paper on your test.
Okay, I'm gonna draw right right here, cause
Yeah, just put it wherever. Put it wherever you want to put it. We're gonna figure it out. Come on, it don't matter. Look at my handwriting. I can't judge you.
Okay.
I can't judge you at all. So go ahead.
So it's gonna be one right here.
Yes,
one
that
right
didn't change.
here,
Yep.
and then
Where's your
right
radical going?
right there.
Boom.
I
I
tried
see
to.
it. Nice work.
Okay.
Yeah, that's right. I'm gonna redraw it, but I just you gotta have a feel for it yourself because you're gonna have to do it when you're taking the exam. You feel me? Boom. So that's the next resonance one. But you're right. You're 100% right. And thank you for putting that on there. All right, so we're gonna stop here. You need to get this handout and work through these examples of these radical allylic radicals, drawing the resonance forms for them. Because again, it's like when we first learn resonance, it's a skill that if you don't have it, then when it's time to use it, you're gonna be up the creek. So it's something that you need to practice often so you can master it. Like this is I threw this example in because I already knew that there was gonna be some disconnect there. So I try to head that problem off before we got to it. But you need to get this handout. It's in the assignments folder. It's under in-class handout submissions, and it's like the third or fourth handout that's there. It's entitled Allelic Bromination in-class exercise, something like that. You need to download that and work through these resonance examples. When we come back on Wednesday, we're gonna be working on this handout, going through the reactions that are shown up top. So, and that first reaction is going to be a pretty long, because we're going to go through the mechanism, and it's going to be a pretty long mechanism, right? Because you're going to get multiple products, because you got multiple allylic sites. All right. Anybody got any questions? Thank you, Joy. I appreciate that. Anybody got any
No
questions?
problem.
Yeah, about anything.
Oh, I had a question. For number 3 on the bonus,
Mhm.
can you like share a video about drawing stereoisomers?
For number 3,
Yeah, it was like how many stereoisomers are there, and then draw them all. And I think that's when you do like 2 to the end, and it was like 3
let me find it because I
stereocenters.
may have I posted that. Let's see. This one right here.
Yes.
So
Wait. Yes.
well, we gotta. If you're not, I see people have already logged out, but yeah, we're done with everything else. So if you need to go to your next class, by all means, do it. So for this, you would draw the mirror image of it, right? That would be 2, and then you could draw 3 diastereomers, right?
I
Hold
don't
up,
know.
all right. You got real quiet, so hold up. Let me see if I can get up. I'll do it on. I got a blank page right there. Perfect. All right, so that's the first image, and then this would be the mirror image. Let me zoom in, make that neater. So this would be the mirror image. That's chlorine, OH, and the carbonyl. You following that?
Yes, but why do the like the staircases turn into the solid
Because the
wedges?
mirror image is the exact opposite of the original. So anything that's wedged in the original image is going to be dashed in the mirror image. Anything that's dashed in the original image is going to be wedged in the mirror image. Right?
Okay.
You can draw. I just drew it like this, but you could also draw it like it's looking at itself. Right? Where this chlorine is here, the OH is here, and this will be there like that. You can draw it either way, but I just went ahead and drew it flipped over.
Okay.
Because these two are the same thing, right? It's just turned in a different direction.
So are they both the mirror image?
Yes, this is the mirror. This is the mirror image. Either one of them will be. You could call it the mirror image. Yes.
Okay.
It's just a matter of how you draw it. Like if I put a mirror here and I move. Let me see right quick.
I see.
You see what I'm saying?
Yeah.
If this is looking at itself in the mirror, come on, pen. Right? This is what the image would look like. But if I just draw it with all the stereo centers in the same location, then I have to invert them because the mirror image is the opposite of the original.
Okay.
So those are 2 of your stereoisomers, right? And then you also you can draw 3 diastereomers of the original, right? Let me show you. So you got here. So I'm gonna change this one. Boom. I'm gonna leave these 2 the same. Following? That's 1 diastereomer. Oh, let me put the carbonyl.
Okay.
All right. And then I can draw another diastereomer where I leave this the same. And then I change this because I'm only changing 1 stereo center at a time. Following?
Got you.
Then I got a third diastereomer that I can draw, which will be here, where I change this. But I leave the other 2 The same. Let me see. Make sure I'm drawing it right. Yeah. Come on. Following that?
Mm-hmm.
And each one of those will have its own mirror image. So that would be the other 6. If you draw these
Okay.
3 and the mirror image of each one, that'll be a total of 6 stereoisomers. And then you got the 2 that you started with, the original and the mirror image. So that's a total of 8.
Okay.
Does that make sense?
Mm-hmm.
Yeah. So each one of those diastereomers will have a mirror image.
Alrighty. Thank you.
All right. You're welcome.
Dr. Russell,
Yes.
can you zoom out a little bit just to get the full? Yep. Okay, give me a second. Okay, thank you.
Mm-hmm.
Oh, I have a question. Well, this was on the quiz that I think it was one of the YouTube pop quizzes.
Uh-huh.
I took them, but I just had a question because I didn't want to take it and get it right, but I don't understand it, I guess, on some of them.
Which question?
Let me see if I can share my screen. I think it was on the first one. Hold on a second.
Let me stop sharing so you can share.
Okay. You have a lot of folders.
Mm-hmm. It's a lot of material.
Yep, for sure. Okay.
Oh, hold up. I gotta enable that so you can share it. You should be able to share it now.
Okay, here we go. Okay, can you see it?
Yep.
Okay, I think it was,
Number 4.
yes.
All right. Let me see if I can annotate this.
Wait. Actually, can we do number 7? Because I saw your little comment at the bottom right here,
Mm-hmm.
but the H's are on the
They're both
stairs,
vertical. Mm-hmm.
right? So then that means that rule would not apply,
Yeah, you don't have to reverse it.
right?
So
So
this will
then,
be 1. That's 1. That's 2 down there. And then that's 3 for the top stereo center. So
okay,
it's S
because it goes,
counterclockwise.
yep. And then that bottom one,
Nitrogen is going to be 1.
right? And then 2 would be this top.
That carbon. Yep. And then 3 would be the CH3.
Okay, so why would number 2, the top carbon, why would that go second again?
Because you're comparing it to this carbon. Can you see my cursor? You're comparing it to this carbon right here.
No, I don't see your cursor. You comparing it to
To the CH3 down. Yes.
okay.
So the next atom would be, even if you go here, you can go to iodine on this carbon at the top. But over here, at the bottom left, the next atom is hydrogen. So that top carbon is going to be higher in priority.
Okay.
So that will be counterclockwise. I'm sorry, that would be clockwise. Right? Because this is going to be 1, that's 2, and that's 3.
Yeah, counter. So then that's
That's
so it would have been S.
That's counterclockwise. Yeah, it should be SS.
Okay.
Yeah.
Wait, let me see this attempt because I could have sworn I answered. S with that one. That was on number 7.
Mm-hmm.
Oh, I answered RR. I did it backwards.
You reversed it because of you probably got the hydrogen rule confused.
Yeah, because I mean, I saw your comment at the bottom, and you said that the stereocenter would be R according to the rule for H being on a horizontal line.
Yeah, that's a typo because that was probably copied and pasted from a different question. So that's
Yeah,
my fault on the feedback because I
that's
think it was dealing with number. Go scroll up to number 6. See, it's the exact same comment. I'll fix that. That's my fault.
no, that's fine. I was just like, H isn't on a horizontal line, so I was very confused.
Yeah, my bad on that.
Okay, that's fine.
I'll go in and edit that because that might have it might have confused others too. But
Yeah,
you saw that H was vertical, so
yeah.
you know not to apply that. That was just a typo on my part.
So even if the H is vertical and it's not wedged, I mean it is wedged, then it would not apply.
It won't be. But see, if it's on a Fisher projection, if it's in a vertical position, it's going to be dashed. That's just the nature of how a Fisher projection is. It's a 2D depiction, but the vertical positions are dashed and the horizontal positions are wedged. It's like looking at a carbon from the bottom side of it, or looking at the atom from underneath it.
Okay.
Mm-hmm.
Okay. And if our test is Wednesday, okay, do you have specific office hours, or could we just email you when we could meet if we have any other questions?
Yeah, just email me.
Okay, sounds good. All right, bye-bye. Thank you.
All right. Thanks. Have a good day.
Thanks, you too.
All right. All right. Sorry about that. That organic 2 at 9 o'clock, man. I get tons of questions. I should have moved this class to a different time, to 11. All right. I see your message. I see your message, Jonathan. Appreciate that. All right. So where did I have? God dang it. I gotta pull your thing back up, Sam, unless you have it close by.
I think I might be able to pull it up and share my screen. Let me see.
Okay. I have screen sharing on too, so you can go ahead and do that. Okay, got you. Perfect. All right. So you also did the Claisen, but you did the traditional, the Claisen that's a 3-3 sigma tropy. So what did you take from this? Oh, let me hit the record button too. Was already recording. Hold up. I gotta